Now that we understand how to generate a Grignard reagent and what reactions Grignard reagents undergo, namely the reaction with carbonyl groups and the reaction with epoxides, we can start to look at the applications. Namely, how can you use a Grignard reagent to solve a synthesis problem? And a relatively simple problem would be to provide starting materials that can be reacted together to give the product depicted on the screen here using a Grignard reaction. So how do we crack such a problem? Before I go into the solution, I want to give you a side note, which is that these problems may and frequently will have more than one correct solution. So one thing that I can do, as you'll see in a few minutes, is add further constraints to the problem. Either how many carbons your starting material can have, or in some cases exactly what starting material you're allowed to use, in order to narrow down the number of solutions. So the first step is to look at the molecule and determine the most logical carbon-carbon bonds to form in the Grignard reaction. Well, anything that we're going to form using a Grignard reaction is going to be an alcohol. So the bonds that you're going to want to form, if you're going to do a Grignard addition to a carbonyl, are one of the bonds that end at the carbon containing the OH. So looking at another picture, we can either form the bond shown in blue or the bond shown in purple using a Grignard reaction. So since this alcohol is a secondary alcohol, the Grignard reagent will need to react with an aldehyde. Remember, we went through that little table in the last lesson as to what kind of carbonyl group needs to react with a Grignard reagent to produce what kind of alcohol. So our options are the blue disconnection. Disconnection is organic chemistry ease for just which bond are we going to form in our Grignard reaction. So the blue disconnection has us starting with phenyl magnesium bromide and isobutyraldehyde. And the purple disconnection has us starting with isopropyl magnesium bromide and benzaldehyde. So if the problem said to use starting materials with 6 or fewer carbons, the blue disconnection would be the only correct answer. Because in that case, the 10-carbon product is broken up into a 6-carbon fragment and a 4-carbon fragment. For the purple disconnection, the 10-carbon product is broken up into a 7-carbon fragment and a 3-carbon fragment. So the second step, once you've done your analysis, is to write out the details in the forward direction, showing all relevant reaction conditions. So what do I mean by that? Well, you start by writing your 2 starting materials, phenyl magnesium bromide and isobutyraldehyde, and then you write your normal arrow and say, first, we're going to mix these 2 starting materials together in ether as a solvent. Okay, remember that ether is the solvent that you have to use for Grignard reactions, as we discussed in the previous lesson. And then after that reaction is complete, we will add H+ protons and H2O in order to put the hydrogen onto the oxygen. And then finally, you draw out your product. Okay, note that when writing out the answer to a synthesis problem, do not write out the mechanism. Okay, there are 3 fundamentally different types of problems that you have to solve involving organic reactions. You have mechanism problems where you are given the starting material and the product, and you need to show curved arrows to show how the starting material gets to the product. That is the only type of problem in which you need curved arrows. Secondly, you have predict the products problems where you're given 2 starting materials and you have to provide a product, but you do not need curved arrows in this case. And then in a synthesis problem, you need to show which starting materials you want to use to get to a given product. And once again, there are no curved arrows involved in the solution to this problem. Okay, let's look at one more example in this lesson, and that is to prepare the following compound, which, if you think back to nomenclature, you should be able to recognize it as being 2-hexanol from starting materials of 3 carbons or less. Okay, so now I'm giving you the constraint, and that constraint is going to dictate which reaction we use to solve this problem. So it's a 6-carbon molecule, and the only way that you can form it from starting materials of 3 carbons or less would involve bringing together 2 3-carbon fragments. In other words, we must form the carbon-carbon bond indicated in red. Well, whenever you see an alcohol as the product, the first thing you should do is consider whether it can be formed by addition of a Grignard reagent to a carbonyl compound. Carbonyl compounds are really, really common. There are many ways to make carbonyl compounds, many of which we will discuss in the second semester. But in this case, the answer is no, because as we discussed in our first example, the bond, when you can add a Grignard reagent to a carbonyl compound, the bond that you want to form needs to end at the carbon containing the OH. And in this case, the red bond does not end at the carbon containing the OH. However, if you think back to the previous lesson and what kinds of products Grignard reactions form, an appropriate carbon electrophile for this reaction would be an epoxide. So let's look at the solution. So first of all, whenever you're asked to solve a synthesis problem, you do your scratch work, which we call a retrosynthesis. So what we say is that the 6-carbon alcohol can be broken up into a 3-carbon Grignard reagent plus a 3-carbon epoxide. Now note I put a funny little double arrow there. The double arrow is what organic chemists refer to as a retrosynthesis arrow. It is different from an ordinary arrow that you use to show starting materials becoming products. The double arrow means this product can be made from these starting materials. So as I wrote in the notes here, it roughly translates as is made from. So if I wanted to translate this equation into words, I would say 2-hexanol can be made from propyl magnesium bromide plus propylene oxide. That would be the name for that epoxide. Okay, so the retrosynthesis arrow is used by organic chemists in the scratch work for solving a synthesis problem. But the final answer with all reagents and reaction conditions must be written in the forward direction using normal reaction arrows. So let's see what this looks like. We take our 2 starting materials, put a regular arrow, single arrow, say that initially we're going to mix these together in ether. That's what the 1 ether means. And then secondly, after that reaction is finished, we will add acidic water, do the aqueous workup, and that will give us the final product. So that's one-step synthesis. In the next lesson, we will move to multi-step synthesis problems involving Grignard